All right. So suppose we are given function f of x. For the moment, we're not going to assume f is convex or not. And we wanted to, let's say, find min of f of x unconstrained. What's the necessary condition or sufficient condition we have for ourselves? We would like to find a point x star such that fx star is equal to 0. That's like bare minimum. Okay. So if I actually want to find something like this, how would I actually go ahead? Until now, we have only looked at conceptual things. What are the properties, this, that. Now, in fact, if I give you a function and ask you to find an x star, what would you attempt? How would you actually go ahead and find it? Okay. Will a computer understand numerical analysis? How would you actually go about finding such an x star?
There are some techniques like find roots of a function.
Okay. So what are those techniques? Give me one.
Bisection.
Okay. What does bisection mean?
Very
You don't have to remember anything. You have a problem in front of you. Apply whatever you can and tell me an answer. You don't have to remember anything. This is the problem given to you. There is a function f, and all you want to find is a point x star such that the gradient is 0. Assuming gradient exists, all those things are given. Sorry?
Take an interval.
Yeah.
Like if on one side it's negative and then take an interval A.
Yeah.
F of A is less than 0 and f of B is less than 0.
Yeah.
And if f is continuous, then yeah, so f of A is less than 0 and f of B is greater than 0, or vice versa, then there exists a root inside an interval. So then you take the midpoint.
Okay.
And either the midpoint will again be greater than 0 or less than 0. So if it is greater than 0, then it's the root is in.
You just repeat with appropriate changing of the interval. Okay. What else can you do?
That is one.
That's one thing. And what kind of guarantee will you get? In the sense, how long will it take for you to find such a point?
So if it takes, we're taking A comma B, then it becomes, in each step we are having. So, so log 2n.
Okay, but can you reach x star doing this?
You only get an approximate.
Yeah, so that's also important, right? You'll always get an interval depending on how much you're comfortable with. So if you have a tolerance interval of delta around x star, your complexity bounds will depend on delta. But how long does it take to get into the interval of delta around the x star? Okay, so bisection is one. What else can you do? Sorry? Don't tell me names. What is the basic idea? So that's why I don't want to recollect anything. Just think on your feet. Lots of approximations. You could use any of them.
I know what this is.
What's the first approximation that comes to mind when you're talking about functions? Linear is one, but yeah, so suppose you use Taylor series approximation. What will happen? Can you build an algorithm using Taylor series approximation? Degree 1. What's wrong with degree 1? What will you get? So think of, rather than saying del f of x star, just think of a function whose roots you're trying to find. So f is essentially del f. See here what you're trying to find, the root of the gradient of f. But think of gradient of f as some new function f. Okay. So all you are trying to find is the roots of this function f. One way is to do dissection, as I said. What other possibilities are there? It can't be that this is the only one, right? So suppose I use Taylor series approximation. Can you build an algorithm using that? You can, right? Guys, come on.
Depends on the interval also.
Why interval?
The second degree in that f prime of c will, if you're taking f of x, it will be.
Just don't even worry about this. Just take a function f. All you're trying to do is to find the roots of f. You have a Taylor series approximation for f. Do what you want. Nobody's stopping you from coming up with an algorithm. Will it work or not? That's a separate story. Okay, we'll get to that. Before that, lots of definitions. Just for completeness sake, many of them you already know. Let x star belong R and the sequence xk also belong to the reals. The sequence xk is said to converge to x star if limit k going to infinity xk minus x star equal to nothing new. You know it for a long time. In particular, what this means for that is for any epsilon greater than 0, there exists a k bar such that xk minus x star is less than epsilon for all k greater than. Okay. Now something new. If in addition there exists a constant beta, where beta is between 0 and 1, and a k bar such that for all k greater than k bar, so do we have xk plus 1 minus x star is less than or equal to, equal to is fine, xk minus x star. What would you like to call it? I'll give a name anyway. So not only this is happening, the difference between successive iterates compared to the limit is decreasing at a rate beta essentially. What would you like to give a definition, name of this type? Is then xk is said to converge linearly. Okay. So this is very important. We'll keep seeing this again and again and again. So this is also called geometric. So that's the funny thing. It's super confusing. See what is happening? Just think about it. What kind of sequence is this? What extra power does it have over this? That should be clear that why we want something like that. So suppose beta is half for a particular thing. What's happening?
The distance between any successive term will be lesser than half of the distance between
Okay, so suppose this is my x star.
from x.
This is my x skip. This is my distance. So my xk lies to the right of the half. And this holds for all cases. You just see what's going on. How quickly is it going to converge? That's why we care so much about. The next step is going to be even further here. And so on and so forth. That's why there's so much importance given to it. Not all algorithms will converge linearly. It's also called contraction. I like to use the word contraction because what is happening is it's strictly getting contracted in each step with a fixed. So beta doesn't depend on anything. Beta is of constant. If beta depends on k, it's a different beast. You'll think of that next. So here, if I make beta k dependent, I don't tell you how it is behaving. It need not be linear because I could make it very slowly changing, very close to 1. Suppose it is 1 minus 1 over k. You would not like that. Right? Definition. So this is also called geometric. To avoid this strange linear and geometric, I prefer to use the word contraction. Okay, so this is an add-on definition. If for some sequence beta k such that beta k goes to 0, we have xk plus 1 minus x star be less than equal to beta k xk minus x star for all k greater than k bar. Exists k bar. Then this is called superlinear convergence. This is even faster than, because now beta k itself is going to 0. The example I gave of 1 minus 1 over k is going the other direction, is going towards 1. So any example here, 1 by k would work, for example. This is rare. And finally, let me not belabor the point, xk plus 1 minus x star is less than equal to beta times xk minus x star to the power r, right? For r greater than 1. What would I like to call this? essentially just called converging with order R. So is this stronger than this? Why? Okay. So from here I can get here by choosing beta k equal to xk minus x star to the power n. How about this way? And when R is equal to 2, it's called quadratic convergence. You can do this all with xk being non. So I started with xk belonging to the reals. You can extend this easily to Rn. There's no difference. Just replace all the mods with norms. Okay. So any example? Examples. Linear convergence. Is the linear convergence clear, or should I go back? Okay. You should always have an example, right, to keep in mind what linear convergence means. Linear is just contraction. That's all. So give me a sequence which contracts. 1 by 2 power n. So let's call it xk. Okay. And what's the beta? And what is x star? Okay. Any more? What property should be true for linear convergence to happen? That xk plus 1 minus x star should be less than beta times xk minus x star. Here you conveniently chose x star equal to 0, and in which case it just became the geometric series. If you want a different example, what do you have to create? Otherwise, if x star is 0, everything will look like this. It's simply xk plus 1 is nothing but beta times xk. So what's the alternate way of producing such an example when x star is not 0? Then what happens?
Linear sequence is converges to 0 and then shifted by a constant x star.
Okay, will that work? Because if you have 1 plus something like this, that won't give you that for free. Once you subtract it out, then but eventually it comes down to the same thing. So if you want to produce a different class, you have to work a little harder. Okay, superlinear. So superlinear is when beta k goes to 0.
Okay.
Is that too strong?
This is one idea, next thing is one idea.
Yeah. See that, right? Why it works? What is x star?
Yeah.
And what is xk plus 1 is equal to 1 by k plus 1 times xk. Any other example? All you have to do is to produce a beta k which goes to 0. Here beta is fixed to be half. Here it is 1 by k plus 1. What other possibilities you have?
1 by k to the power k.
1 by k to the power k. But what is xk?
X is 1 by k to the power.
Xk is
1 by k to the
okay. What kind of sequence is this? Among all the convergences, is it superlinear or even stronger than?
power.
Okay, so what is beta k? By k? No. What is xk plus 1? 1 by k plus 1 power k plus 1. So how much is remaining? Yeah, it's order 1 by k, not exactly 1 by k, but okay. What about quadratic? We're trying to map the two, right? Superlinear versus quadratic. Will this work for quadratic? 1 by k factorial?
You can use double exponential. 2 to the
No, no. I'm just trying to point out, you're saying something about going from here to here. So here to here, sorry. Will this work as an example? It's not equivalent. So something like, let's make it 2 power. So can you use this to produce a sequence? That's the first time, yeah. Something to the power 2 power k. What is that function? 1 by 2 power k, right? Now if I make it something like this, alpha to the power 2k, where alpha is between 0 and 1. What kind of function is this? Is this order wise going faster to 0? See, that's all we're really going after. Every improvement, we're actually making an order wise improvement. When we just said convergence, we never cared about how fast I'm going. Linear gives you that I'm going at least a fixed contraction. This gives you that the beta k itself is going to 0, even faster than that. Now this is even more. So what does it satisfy the quadratic condition? This example. What is the quadratic condition? That xk, x star is 0 anyway here. So xk plus 1 is equal to xk square. Does it satisfy? Is everybody convinced? What is xk plus 1 by xk square? Let's take the ratio. No? How do we add things? When you're multiplying powers, we simply add. That exactly gets you 2 power k plus 1. This is a quadratic. Now tell me what is xk is equal to our humble 1 by k. What kind of convergence is this? The most humble. Which one should we try first? Strongest or the weakest? Okay, so does it satisfy in linear?
There's not really.
There's no beta less than
Because
because I have that xk is plus 1, it's just 1 by k plus 1, which is less than 1 by k.
is that convincing?
No, it is thinking like xk plus 1 is equal to 1 by k plus 1. And 1 by k plus 1 minus 0 is just 1 by k plus 1. 1 by k. So if say if possible, let there be a beta such that.
No, so what is the ratio of the two sequences? 1 by k plus 1 divided by 1 by k. What is it? K over k plus 1. That's all you have to worry about. What kind of sequence is this? So can there be a beta? That's all. But you have to convince yourself that 1 by k. So if you show something like this is only converging, nothing more than that. We generally are happy with this, but in terms of what we're after, it's not very useful thing. Okay. So now in this, with these definitions, where does the bisection method lie? Right? Okay, so let me just, so suppose f is a function whose 0 we are trying to find. So don't confuse between f and the gradient of f. I'm not trying to minimize f, I'm trying to find the 0 of f, where I've gone one level up. It's a gradient, so f is nothing but the gradient of f. We're trying to find. So f might look something like this, possibly. Who knows, multiple zeros. So to get rid of that, we'll say it's a univariate function. What is the univariate function? Know what a univariate function is?
Only one variable.
Okay. But is this okay? If I have the function of this type, is it okay? While finding zeros? Okay, right? So if I want to restrict to having 1, 0, what would I call it? Like suppose the function, the class of functions I want to look at has only 1, 0. You've heard the name unimodular by any chance? If not, forget it. Okay. So think about a single function and let's say this is your f. Now what is the bisection? You start with, let's say, right interval b and left interval a. And what do I do next? Won't you have problems? For such a function, won't you have problems executing bisection? Okay. So what do I do? Because your algorithm highly dependent on what is the value of function here and what is the value of the function on the left. It could be both positive, could be both negative. So how do I fix that? You'll have to restrict yourself to having a single root. There is no other way. If there are multiple roots, bisection is not going to give you unless you do something interesting. So we'll worry about functions of that's the only function I can really handle. And this is okay if you remember convex function. We're looking at the derivative of the convex function. Don't think that normal convex function doesn't satisfy this. This is not f, this is gradient of f. Okay, so now suppose there is a single row. Now what will I do? We start with the a and start with the b. Supposing this is the thing, this is negative and this is positive. Now what should I do? Which direction should I go? Yes, so I have f of b and I have f of a.
F of A is less than 0.
Yes. Yes.
So now we need to record the thing.
Okay, so I go to a plus b by 2. And now what should I look at? Whether it is less than or greater than. So suppose in this case it is less than. Then what should I do? I'll just shift a to a plus b by 2. And this is my new interval. And I keep doing this repeatedly. Okay, what guarantee can you give me on this?
Yeah.
That of convergence.
How fast?
First of all, even does it even converge? Why?
Intervals are getting smaller and smaller. So then you for any epsilon you have there is a
Yeah, but
epsilon will have an interval that is smaller than epsilon.
you never said the function was continuous.
Yeah, I mean giving that a better comment.
Okay. So given that the function is continuous, what is the guarantee you can give me?
The interval becomes perfect in that direction.
So you can use the notation now we developed for ourselves. Xk plus 1 minus x star is exactly half of xk minus x star. That's it. Just brutal. There's nothing more to be done. So as long as it is continuous, single root, it will work out. But non-continuous, is discontinuous, you can't say any of this. Things will become difficult for you to say. Okay, so then we go to the next method, which is called the Newton's method. So again, you have the f, you want to find an x star such that x star equal to 0. Again, let's just take that. Okay, so that's your f. So think of Taylor series and try to come up with an algorithm which is reasonable. We'll worry about what guarantee we can give, but at least come up with an algorithm. Gaussian bisection out of the way.
Taylor series would be like, let's say that the dimensions
Yes.
of y would be like x. If prime of x times y minus x.
But think of this geometry, right? You're trying to find this point. You have no clue where it is, but wherever you are, what does it look like? How to reach that point? What is it? So suppose I'm looking at this point x here. What is the Taylor series approximation from x has anything to say with respect to me reaching f of x star equal to 0 or x star?
It is going down in the direction of
But I don't know if it's going down. All I know, I'm here. It could be that it possibly I just flip it around. If I flip the function. But what does the Taylor series approximation at x mean? Which is a gradient approximation. That's all it does. So what would that be?
f of x plus
Mhm.
x square.
Should be f of x is equal to f of x0, some point x0 plus
F prime x 0.
del f x0. Now, what are you looking for? You want to looking for a point at which f of x star is 0. So what update you can make? So suppose you're starting from a point x0. What should be your next point in hope of finding a 0? I'm not saying you go there in one step. So suppose I've written equality anyway there. It's not equality, it's Taylor series. Suppose it was equality. And if I ask you to find an x star such that f of x star is 0, what would you do? How would you choose your x star?
X naught minus f of x0 by
X star such that the left hand side is 0. Right? As simple as that. Now, because I'm not precise in my approximation, I will only get some approximation error. But if I do this often enough, hope is I should come close to finding an x star. So this is a completely different idea of getting to a root of a polynomial or root of a function x. Your bisection was one idea. Here there is no bisection going on. We are not bothered about how far we are, what value we are getting. All we are trying to say is supposing that the Taylor series approximation is in fact accurate, here is an iterative algorithm which should get me close to x star equal to 0. So what will that algorithm means? So let this equal to 0, f of x0, and solve for x. So this requires differentiability. Let's call it x1 minus x0. That's my next point to probe. So what will x1 look like? X0 plus something. Why this you have seen. Some form of this you have seen. So this is what the Newton's method looks like. Okay. So now what is going to happen to this? What kind of guarantee can you think we can give? What's the good thing about it? What's the bad thing about it? Okay, what are the difficulties you're likely to face executing such an algorithm?
If the slope is zero at some point, then
Zero is definitely a problem. Even if it's very small, you can be in trouble, right? So that's one of the problems. What else can you see might be problematic? So does this choice of starting point matter is the question.
it need not converge.
Why?
We construct the function such a way that and then take the starting function that they just alternate.
Can you construct such a? To think about choice of x star and x zero. Can you come up with a pair where things are bad for this algorithm? So Pranav, if at all there is a problem, what kind of problem will it be?
And as you said, they might keep on repeating that.
Why? If it is repeating, what will happen? Can it do that and not converge?
Maybe take a parabola.
Give me a second. Then it should converge. What is the iterate telling you? It's telling you x0 minus the value of that function divided by the gradient. What can go wrong? Why would it not go towards x star? So try to construct an example where it, rather than oscillating, it even diverges.
It's not very big.
Okay, so
That could go on increasing to construct something like that.
I'm going in the left direction, right? Yeah. You have an example?
Yeah, we take the parabola.
Okay, let's take a parabola. Here is fine. This should help. Okay.
Let's say like something like x squared, it's like alpha x.
Okay. F of x is x squared.
And let's say that x naught is somewhere on the right plane. Yeah. So what we can choose that if we take the x1 can be on this side. And we can,
Okay, tell me how.
like x naught, x1 equal to minus x naught.
X1 is equal to minus x naught. How do you produce something like that?
Yeah.
Parabolas are convex.
Yeah.
So every supporting hyperplane will be an unconstrained.
It will keep going downwards, right? You will not be able to produce something which goes back there.
Obviously to the right of them.
That's not going to happen. This will definitely come something like here. Then this will go here, and so on and so forth. What you want is to produce x0 which is far away from x star, at which time this actually starts to go away from x star. Does it even appear possible? But why I'm hammering on this aspect is many of the algorithms will prove if you start close, you converge. If you don't start close, there's no guarantee. Many of the algorithms we will discuss will have this flavor. So it's important how far you are from the optimum, which is kind of self-defeating exercise. But that's the guarantee you can give. That if you start close enough, you'll converge. Okay, so anybody else? Otherwise, exercise. Choose x0 far enough from x star and show the algorithm diverges. Okay. Okay, so what we will do is, sure,
What if we try and then log of x?
you can try anything you like.
We can choose something like
Okay, what is the function?
dot.
Log x.
That's a different one.
Okay,
Okay, but its slope is not necessarily, its slope is never decreasing. It's not.
I don't know what-
Negative. 1 by x is not. Positive value is not. It's
the
not
slope is
negative.
decreasing.
Yeah, slope is not negative.
Yeah.
And also the domain.
Yeah.
That's one is the outside domain.
Let's rule out the pathological cases. Okay, so what we are going to show for Newton's method? Two things. First convergence and then we'll say quadratic convergence. Okay. But under certain conditions. So let F to R and we said this, right? This means, what does it mean? One time differential. Let Fx star is equal to 0 and F prime of x star not equal to 0. Then this is the punchline. Then there exists an interval, an open interval rather, S equal to x star minus an epsilon plus an epsilon, epsilon greater than 0, such that for any initial point x0, belonging to S, this is the set S, the Newton method rates are well defined and converge to this is a valid criticism of this kind of guarantees. That if you start close, you converge. Now, how do I know whether I'm starting close enough or not? So that is left open. Okay, so how would you prove something like this? Now that you are given that there is an interval, which is, or you rather want to prove that if you start close enough, so you have choice of epsilon with you to produce, such that if x0 belongs to this interval S, then I will converge. So the conditions are very mild, right? All of you are asking is f is differentiable. That's all. So what does differentiability mean for a function around x star? X star is known to exist. We're looking at a area which is very close to x star. You're supposed to produce an epsilon. You're allowed to produce any epsilon greater than 0. So what does differentiability around x star really mean? That's all the crux of the proof is. What does it give you? And importantly, f prime of x star is not 0. So as soon as you see something like not equal to 0, what is the thing you should click in the mind? That I'm allowed to take by of what? 1 over that is meaningful. Oh, so let's call this as A and this as B. What do the A and B tell us? A and B tell us that 1 over f prime of x is less than equal to mu for x belongs to S, where S is nothing but for some small enough interval x star plus epsilon. What am I doing here? Taking the modulus. I know that f prime of x star is not 0. So this quantity is, I can divide after taking the mod, and there exists a mu. So mu is some quantity, some bound on that. So lots of there exists. Oh, now what can I do? What more do I know about f given a and b? Can you give me a bound on f prime y minus f prime of x to be less than equal to something where y and x appropriately lie somewhere? Is it like, what does it mean for xy? Let's say xy belonging to S. How much this should be? See, what this means that the derivative is continuous. That's what it means. So derivative is continuous. What can you say for an x and y belonging to S? Less than equal to, can I do this for some alpha less than 1? Okay, not okay. All I'm using is A and B, nothing more. And mu is greater than 0. But I'm not clear why any of this is true.
How do you get that?
Just A and B. So tell me, if f prime is continuous, what do you get? If I look at, and f prime of x star is non-zero, and f prime is continuous. So you're looking at this interval, x star is here, this is x star minus an epsilon and x star plus an epsilon. This is my S. What does differentiability give you? The continuity of the derivative. Let's just focus on this one. If I just told you that the derivative is continuous, what can you say? That there exists, what is our brutal definition? There exists an epsilon such that for all delta, this is true. That's all I'm doing. I'm choosing epsilon, I'm choosing this. So think of this as delta. And now, given that this is also non-zero, I can just plug the same thing over here.
The mu is same.
Yeah.
Both of them.
You choose one mu and then you do the other way around. See, all of this is my choice, right? I'm picking an alpha small enough, mu small enough, whatever I want. So here mu large enough and alpha small enough. Epsilon small enough. Everything is under my choice. I'm not specifying anything because my theorem doesn't require anything. All I'm saying is there exists an epsilon. such that for a small enough interval, if I start inside that, I can converge. That's all. So let's call this equation number 1 and equation number 2. This has nothing to do with Newton. This is a basic fact from the function being differentiable. That's all. Is everybody okay? This is the first thing I would like to write. And the second thing I can derive from there. Okay. Now given 1 and 2, now you marry this with your Newton's update. What does it tell you with respect to the Newton's update? What is going to happen? What was the Newton's update? Was xk plus 1 was xk minus f of xk divided by del f of x. Right? So I can write this as xk plus 1 minus x0, because that's what I'm interested in to prove convergence. Xk. And now what can I write f of xk as? F of xk minus f of x star, because f of x star is 0. I'm just writing something which is 0 minus f of x star. So what can I write this as? Del f of xk times xk minus x0 minus f of xk minus f of x star divided by derivative of f of xk. Okay. Now what should I do? I can take the modulus on both sides. What will I get? I'll simply get mod of this will be mod of this. What about downstairs? Okay. Now you can use equation number 1 and 2 somehow. What have we derived for ourselves? This and this. So how can I use it? Get rid of the denominator essentially and put a mu times this. Okay, how do I make further progress? Remember, I want to prove convergence. Doesn't remind you of anything. What kind of terms do I have on the right hand side? I have f of xk, I have f of x star, and the first thing, have I made a mistake? It should be x0 is fine. Okay, so instead of x0, we should have taken x star. That's what I really wanted. Nothing is wrong here. just 0 should be replaced by star. Star here, X star here, X star here. Now look at this. This is f of xk, f of x star, del f of xk times xk minus x star. Any inequality or any theorem you know which connects these things? Not the convexity. We're not assuming anything about convexity. Rolle's theorem, you remember all those calculus theorems. Any theorem which comes to mind which can bound this? Sorry? So let me write. That is called the lemma integral mean value theorem. Let f be R to R and f belongs to then for x and x plus h, f of x plus h is equal to f of x plus x to x plus h f prime of ut. So resulting is f of x plus h minus f of x minus h times f prime of x is equal to x to x plus h f prime of u minus f prime of x. Just rewriting this, subtracting fx and as well as h times f prime of x, adding it back together here. And alternatively, you can write f of x plus h minus f of x minus h f prime of x equal to h times 0 to 1 f prime of x plus lambda h minus f prime of x. So these are equivalent once you get it. So I'm not going to prove this. It's just a basic fact. So this is the basic fact. Okay, so now given that we have it, how do I use this in my... So look at what I want. I want to control f of xk minus f of x star in terms of del f of x, xk minus x star. So I just wrote the final form, which is what I'm going to use here. So mu times x star minus xk integral 0 to 1 f prime of xk plus lambda x star minus xk minus f prime of xk. Okay, that's what we just wrote, the final one. That's the form I'm using here. Now, any idea how to get rid of this integral? Because the integral is over 0 to 1, I can just take the max of lambda over 0 to 1 and replace the integral. That's all I'm going to do. So the answer will be mu times, so is less than equal to mu times mod of x star minus xk super for all of this. Actually, max is fine, but let's just. All right. So, what have I got finally? That xk plus 1 minus x star is x star minus xk, which is the same thing, xk minus x star. Mu, which is less than 1. And what about this quantity? Why is this less than equal to 1? That's all you have to argue. Look at the terms inside. F prime of xk plus lambda x star minus xk minus f prime of xk. It should click now. That why did I insist that my points are lying in S? See, what do I want? Mu times the supremum to be less than or equal to 1. No? If I want to prove convergence, what do I need? This less than or equal to this is not sufficient for convergence, clearly. So what do I need? Mu times the supremum should be how much? Less than 1. But go back to my condition number 2, if you have in your notes. Mod of f of x minus f of y. When both x and y are in S. So if I apply this, what will happen? This is nothing but f prime of something which belongs to S as long as xk belongs to S. See, x star by definition belongs to S. So as long as xk belongs to S, this is nothing but a linear combination. So it belongs to S. Xk by definition belongs to S. So my condition number 2 applies that no matter what x and y's are, the difference is at most alpha by mu. So mu and mu will cancel, alpha is less than 1. So that is where it critically depends on where you start. So this is less than or equal to mu times alpha by mu x star minus xk from 2. And all of this is critically dependent on as long as all these xk's. So beginning, the first one, as long as it depends, as long as it belongs to S, everything else will follow. So that is why I insist that x0 belongs to S. So if you start within a small neighborhood, you remain within a small neighborhood and you converge because of this. You can ask it's a useless guarantee, but that's how it is. That I need to ensure that I start close and then I converge. All right. So final punchline, that if you in addition assume something, so additional assumption. Any questions? Any question? I'm happy to slow down. Just tell me. The good thing is already everything is in the video. So that's, I think, actually like this. Have you written up? So f prime is Lipschitz in addition. Let's put the spelling SCHIPZ. So what does that mean? That f prime of x minus f prime of y is less than or equal to L times x minus y. That's what Lipschitz condition means. For all x1 in S. S is the same as before. Okay, so if you assume that f prime is also Lipschitz on S, then I claim you should be able to show quadratic convergence. What are the quadratic convergence? That xk plus 1 minus x star is less than or equal to something times xk minus x star whole square. So how do I? So now we go back. We are here so far, right? So now if we, in addition, if you assume that it's Lipschitz, what will happen? See, what have we established? You established mu times this times the supremum. That much you established without that assumption. Now, if I throw in that assumption, what more do I get is the question. Okay, very good. Okay, is that all? What does the Lipschitz condition mean? F prime of x minus f prime of y is less than or equal to L times x minus y. This by definition belongs to S. So this point by its very definition belongs to X. So that should apply. But is that all or is there something more? Does everybody see it? By what am I doing? This is a condition which is telling me that f prime of x minus f prime of y is less than L times x minus y for any xy belongs to S. I'm so far here. What have I got? With the supremum, forget the integral. Supremum, the same thing is sitting over here. So let lambda, so you have to establish that the only thing you have to establish is that the max is actually achieved. And that is not difficult. Okay. So choose the lambda which achieves the maximum so that you can get rid of this also. And that lambda is such that this term belongs to S. This by definition belongs to S. So you apply the Lipschitz. What did you get? Mu times this times lambda times x star minus x. And that's how you'll get mu times lambda times the square. So you'll get a quadratic convergence. That's all the proof there is. But still, you're not able to get rid of the fact that you have to start close. So starting close is still a requirement. Start close, you converge either normally, just converge, or you converge quadratic. So the speed of convergence is very fast with Newton's. It's just that it's a very strict requirement of starting close. So next what we'll do is we'll take the best of two worlds. What was the bisection? Bisection didn't care where you started, but the speed is slow. It only does it at a rate 1/2. It's always linear. This can get you quadratic, but you have to stay close. When you get the best of both worlds is what we will discuss next. Yeah, so now let's say if I can replace this soup, can I actually cut this? By a max. All right. Now there will be some max lambda star which will maximize this. So replace that whole thing with f prime of xk plus lambda star x star minus xk minus f prime of xk. From my Lipschitz condition, what do I get? I just get this term multiplied by the Lipschitz constant. And what is that term? Mu times lambda, right? If we can go forwards, f prime of x minus f prime of y is at most L times x minus y. So it is lambda x star minus xk. Lambda is between 0 and 1. So I'm okay. Mu times lambda times n times the square of this. That's all. And that's how we established quadratic convergence.